Hi, everyone. Thanks for joining us for our first talk of 2022 and the kickoff to our series exploring cyber resilience. And for our cyber resilience series, we are very lucky to have SERC Research Council member Dr. Peter Beeling. Dr. Beeling is a professor in the Grado Department of Industrial and Systems Engineering and Associate Director of the Intelligent Systems Laboratory in the Hume Center for National Security and Technology at Virginia Tech. In short, he's a thought leader in the field, and we thank you again, Peter, for curating and moderating the series.
My pleasure. Thanks so much, Mimi. It's an honor to introduce our speaker for today, Dr. Eric Vugrin, who is a distinguished member of the technical staff in the Cyber Resilience Research and Development Department at Sandia National Labs in Albuquerque. His research focuses on the development of analytical tools and methods for modeling, analyzing, and designing resilience in complex systems. Cyber and space systems are his current primary applications of interest, and he's previously worked on supply chains, public health systems, power systems, transportation networks, and other critical infrastructures. His work has provided support and guidance to research, operations, and policy groups at the U.S. Departments of Homeland Security, Defense, Energy, and other agencies. So that's a really broad list of things that I think will be of great interest to this audience. So it's a real pleasure to welcome Eric. So Eric, welcome, and thanks so much for joining us. And please feel free to take it away whenever it's convenient.
All right. Well, thank you, Peter, and thanks, Mimi, for setting this up and getting us kicked off. Really interested in the topic this year of cyber resilience. It's something that's near and dear to my heart and has been kind of an intense focus area of the last 5 years of my research. So today I want to talk about how we go about modeling attacks and how we model the systems that are being attacked so we can characterize resilience of infrastructure systems. And my academic background is as a mathematician, and I would love to write all the equations and get down into the nitty-gritty details of how we actually do this. And if that's what you're hoping for, I apologize in advance. I'm going to disappoint. Rather, what I want to do is kind of bring up a variety of techniques and tools that we're using at Sandia to investigate cyber resilience. And so I'll give a taste and a flavor of a lot of these, but not dive too deep into any single one. And if there's a topic that you would like to hear more about or get involved, we can certainly discuss that in the Q&A, or I'm happy to follow up offline and we can get into some of those details. But before we hop into how we model them, I want to start out with a little bit of motivation as to, at least in my opinion, why cyber resilience, and particularly for critical infrastructures, matters. And we don't even really have to think too hard. We can go to the open news publications to see a variety of attacks that have happened just in the last decade. So the Colonial Pipeline was attacked just last year, shut down due to a ransomware attack. Everybody knows by now the Stuxnet attacks in 2010 that affected the Iranian centrifuges, maybe a little less well known in the general population, but certainly timely with the geopolitical events happening right now. In 2015, there were hundreds of thousands of people who lost power due to a cyber attack in Ukraine. And so 20 years ago, if we were talking about cyber resilience of critical infrastructures, it would have been a purely theoretical academic conversation where we could explore, but there wouldn't be any evidence in front of us. Today, it's not a theoretical discussion. It's really a practical reality that we're dealing with. And with the increasing number of attacks, we need to be increasingly thinking about how we can make these systems resilient. So if I'm an infrastructure operator, on a daily basis, I'm probably getting reports and notifications on this is the latest cyber attack that you need to worry about. And the hard reality for critical infrastructure operators is they really don't have the time and resources to protect every asset all the time against every threat. And so a real challenge that they face is how do they prioritize planning and mitigating for these attacks. And so an approach that we have taken at Sandia is trying to figure out, can we use mod sim capabilities at the lab or developed outside the lab, where we can think about how might we model these attacks, how could we characterize the resilience, and is there something we can do to help those infrastructure operators prioritize. And so I'm going to talk about a research effort that we call ADROC, or Advancing Resilience of Industrial Control Systems, that's currently ongoing at the Sandia Labs, where we're trying to answer these questions. And I'll tell you, by the end of the talk, we won't have all the answers. We'll probably have more questions, but you can at least get an idea on how we're looking at this problem. So when it comes to modeling cyber resilience, there's a few things that we need to think about. First off, we want to be able to represent the threat being attacked. And in today's conversation, we'll talk about industrial control systems or critical infrastructures. So how do we model the system? How do we model the threat? A colleague of mine, Vince Urias, likes to say there is no security without the threat. Otherwise, everything's simple and easy. So one of the challenges that we do face is how do we represent the threat within our models and our analyses. And then metrics. How can we measure, characterize the impacts of the threat, the resilience of it? In the very early days of resilience and cyber resilience, it was one of those things where you recognized it when you saw it. But I think the field is becoming more mature, and I know it's a priority not just at Sandia but elsewhere to develop those metrics. And so we'll briefly mention kind of how we think about that at Sandia. The time that I spent in physical infrastructure before looking at the cyber world, we had a lot of these individual models for looking at systems or threats or metrics separately. But I think one of the real hindrances was until they come together and play nicely, sometimes they're too much of a pain for people to use. And so I'll describe how we're integrating this under kind of a single platform to really make the use. And ultimately, kind of, I'll walk through a use case that demonstrates some of the techniques and tools that we're using. Again, I'll provide the highlights, but if you're interested in the more detailed discussion of that, a colleague of mine, Jamie Thorpe, has an upcoming paper that will get into the details of the use case, and I'd be happy to share that with you. So what are industrial control systems? And so many of the folks on the call probably know this already, but a lot of times when I think of cyber systems, I'm kind of thinking of IT, information technologies. And so, it might be my desktop, my laptop, we've got some email servers, we've got our DNS servers, but the main point on IT network is the flow of information back and forth, maybe protecting information. But when we're talking about industrial control systems, it's not merely cyber for information's sake. It's cyber to control a physical process that's actually interacting with the physical world. And so maybe it's power generation or chemical refining or water treatment or transportation networks. But there are some additional elements once we start looking at an ICS or an OT, operational technology system, that we don't necessarily see in the corporate network. So when we talk about industrial control systems, there's usually kind of two main parts. One is referred to as the SCADA network, supervisory control and data acquisition. And so there we might have workstations and consoles where engineers can log on and check the system. The SCADA system is really the part of the system where we're going to monitor, we're going to log, and we will do some control. And so we can, from the SCADA network, we have the data historian that's storing things, the SCADA server that might be pulling in data coming in from the network. It might be translating the protocols. But this is the side of the network with which we can remotely interact with what is called the production network here. And so the production network is going to include that physical process. I'll use power generation as kind of our primary example today. But there are field devices out there that are interacting directly with those physical processes. So PLCs, programmable logic controllers, these contain the logic for how should we be operating that physical process. So we might have some logic in there that says, oh, the pressure is going up, so we need to open a valve, or the temperature is getting too high, so let's start the coolant pump and cool things down and maintain a happy equilibrium. So we'll see PLCs, we'll see remote terminal units that are gathering information, passing it back and forth. And the big difference when we're looking at ICS as opposed to our IT networks is both that physical process that interacts with the real world, but also we're going to have a lot more heterogeneity in the types of devices that we're looking at. They might be speaking with different protocols. Over here, we're probably getting a lot of TCP, HTTP protocols. But here we might have Modbus, we might have DNP3, a lot of things that might seem exotic to people who aren't looking at the industrial control systems, but they're going to be different protocols, software, and types of things that we would want to be representing in the industrial control system. So when it comes to modeling these systems, we have a lot of options. And when I first started investigating cyber topics, the folks that are kind of formally trained in information security and protecting our systems, they are almost always most comfortable looking at the left side, at testing and exploring and researching on the actual system. Real hardware, real protocol, stick the actual malware on there, see what happens. And the benefit of that is we have a high fidelity platform. It's a realistic representation, but it does come with a price. You know, when we have the actual system and we've done our tests and gathered our results, we know it for that one individual system. And if we want to change the system or the attack or the mitigations, that can have increased costs. It can take longer. One of the real worries about when we're doing our cyber experiments is if you break a device, it's done. It may not be available anymore. And so you have to go out and buy a new component. Or if we're actually playing with power generation system, you can cause some real damage here. So very rarely does anybody ever say, yeah, run your experiments on my actual platform. So that's where we look at other modeling opportunities. Conventional simulation, optimization, agent-based modeling, it could be solving differential equations to represent a physical process. We certainly use simulation to explore cyber problems. And what that entails is coming up with a mathematical abstraction of what the system looks like. It's not the actual hardware, it's not the actual software, but it's representing what might the effects of an attack be on a system, and through some generally mathematical representation. And the drawback is it is more abstract, and so the question is, as we abstract away from the real system, are we losing some fidelity? Is our model still valid? But the benefit that we get is a lot more flexibility. Computationally, it could run faster in real time. We might be able to build these quicker, cheaper, run them on a large computing cluster, and we could do sensitivity analysis and explore a lot of scenarios rapidly. So one of the capabilities that we've been using for the last 15 or 20 years at Sandia is really kind of this concept of virtualized testbeds, where it's attempting to give us the best of both worlds. So when we log into a platform on the cloud, we're not actually logging into a real desktop or a physical system. What we're logging into is a digital virtual clone or abstraction of hardware that's running the actual software. And so within these virtualized test beds, what we do is we use virtual machines to represent the hardware, and we can run real software. They can speak with real protocols, send packets back and forth. And so what that allows us to do is get greater realism like we want with the actual system, but we get some increasing flexibility. If we brick a virtual device, we just tear the system down, we spin it back up, and we're off and running again. And so we have some of the benefits of more realism, but also some of the flexibility and decreased cost and time for setting these up. And so this is an approach that we've been using a lot lately at Sandia, and at least in my personal investigations. So when we're talking about emulation platforms, another word for virtual test beds, for industrial control systems, one of the platforms that we like to use at Sandia is called Scepter. So Scepter allows us to represent the SCADA side of the network. And so we have virtual devices representing the historians, the servers. You can actually log into human-machine interfaces and interact with the system and see what's going on. These applications are put together with software-defined networking. So again, we could speak some of these seemingly exotic protocols that might not be used elsewhere. And we have routers, we have switches all set up virtually. And so the devices talk back and forth with each other just like they were actual real devices. Now, the secret sauce for Scepter is how do we get these devices now speaking with some of these field devices and with the end process simulation. So what we're able to do is we can virtualize the RTUs, the PLCs that are directly interfacing with some of these physical processes. But instead of interacting with a real world physical process, this is where we set up a simulation. So we can have Power World, which is a model that represents power systems, generation, transmission, etc. It solves the differential equations and whatnot. And so we can have these field devices speaking with the physical process simulations, and the physical process simulations talking back to them. And so the field devices think that they're actually interfacing with a real power generation system. And the model thinks that it's getting updates to its parameters. And so when we put this all together, we have this consistent platform where if we want to model attacks or study the system, we can put in the malware somewhere, watch it progress throughout the system, and then we can see the potential effects on the system through the effects on the simulation of the power system or whatever else that we're looking at. And I say this is secret sauce, but the hope is to make it less secret. We're in the process of trying to make this open source and readily available to the public. We have developed platforms using Scepter to test automated mitigations and response through the Mosaics program for the Department of Defense. We've set up exercise environments for various different large-scale exercises. There's one called CyberFlag that we've created, the ICS platform, and you have red versus blue teams. They're at their laptops. For all they know, they're actually interacting with the real system, and we can actually watch and see what's going on in this particular environment. So Scepter is a nice capability for us to model the industrial control systems. And I mentioned, we can drop malware into these systems. We can actually have humans interfacing with it, kind of acting as the bad guys or the good guys. But when we do that, sometimes we lose a little bit of the repeatability that we would want from cyber experimentation. It might be we have a really smart red team one day and, somebody who's off their game the next day. And so it's a little hard to get the repeatability that we would want from maybe some of our assessments and analysis. So one of the tools or sets of tools that we've been using lately, we call threat emulators. Other people might call them automated pen testing tools, but there's a variety of these capabilities that have been developed from various different groups where you could actually have high fidelity automated attacks for your test bed, and you put them in there, you push the button, and you see what happens. And so one of the capabilities that we've been using a lot on the AdRock project is one called Caldera. It's a MITRE developed threat emulator. And the concept is here, through the configuration of the Caldera tool, you can set up attack profile. So this is the goal of the attacker. These are the capabilities that they have. This is the sequence with which they might employ them. These are the general attack steps that they would potentially set up. any requirements for executing a step. But once you set up the attack profile and the goal, what it's trying to achieve, you can run Caldera on your physical or virtual test bed and see, is it able to achieve the attacker goals? How long does it take, etc. And the benefit of using this approach, as opposed to maybe traditional mod sim, is we're using the actual real attack tools and techniques that have been observed in the wild by hackers and adversaries. And so there's less of an assumption that, yes, the effect will definitely take place. It will be, is this the right tool? Can it actually get this desired effect? And it does it all in kind of this automated fashion. Caldera comes with a lot of these attack tools pre-packaged within it. And so it's not too terrible to set up and use within your testbed environment. One of the limitations of Caldera and most of the automated pen testing tools that we've looked at is they tend to be IT focused. And so if you want to do attacks on industrial control systems, at least in our experience, we've had to add some additional payloads or plugins, and Caldera is nicely extensible in that way. And so Caldera can take us through the enterprise part of the network, but when we're actually attacking the ICS portion, we can actually go ahead and add some tools there. So we've got a means with which we can emulate the system, we can emulate the threat, and then the next step is actually kind of modeling and quantifying and characterizing the resilience of the system. I'd love to spend the next 2 hours just talking about metrics. It's a real topic and interest of mine. But I think what I'm going to do is kind of describe a general structure of how we go about it. And I can point you to some references afterwards on the details of how you might actually introduce metrics. So we try to report metrics for resilience at a variety of different levels. And in our experience, there's various different perspectives we need to satisfy when we're talking about resilience. It could be the general who says, is the system resilient or not? Or, what are the two things I need to worry about? And so we can certainly report scores at an overall system level, 0 being the worst, 1 being the most resilient. And we can certainly provide those answers. But a lot of times, if the general says this is a problem, go fix it, well, then the private needs to understand at a little bit of a different level. And so we look to report metrics across some major areas. It could be, how is the network operating? Are the hosts up or down? Is the mission, the physical process of the industrial control system, is that functioning as expected? Are we aware of what's going on around us? And so we have a number of levels that we can calculate and quantify resilience at. But at the base level, at the device level, these are data streams that we're pulling directly out of the experiment. And so they can tell us how much traffic is going in between two devices. They can tell us if one particular PLC is up or down. They can tell us if we've exceeded safe operating conditions. And so the process of calculating metrics, at least in the context of this discussion, is we'll run the emulations and we'll extract the data from those experiments. And then we have a library of metrics with which we can process those data streams according to how the analyst wants to look at it. And then we can start to report scores at these various different levels. So like I said, I'm giving a really fast introduction into the metrics here, but I'll show some examples of how we think about it in the context of a use case. So the last thing I want to say is I've made my big pitch for virtualized testbeds and emulations and why we like to use them. But one of the challenges with these testbeds is that they run in real time. And so if we want to look at a lot of different scenarios, and maybe the scenarios take 2 hours to go from start to finish on the attack, and we want to look at 100 variants, that's 200 hours right there. And if we don't have a large cluster, we're starting to run into limitations. And so we definitely go to the virtualized testbeds when we want our high fidelity results. But under AdRock, we are also using some mod sim, some mathematical modeling, to do some filtering down of threats, to go from dozens of concerns to maybe a handful, where we can use kind of our high fidelity approach. And so the concept that we use here kind of represent in our ad hoc workflow. So imagine, we're doing our research and somebody says, here's the 100 threat reports that have come in through the last week. We want you to analyze them and tell them which ones we need to worry about. And so it's too much for us to jump straight into the emulation side of things. And so we've employed the use of some lightweight mathematical modeling techniques called Markov decision processes, where we can build these models relatively quickly. They're computationally efficient, and this particular modeling structure allows some of that attacker-defender interaction, the interplay that we would expect to see in a cyber attack. And so what we'll do is we'll build a model for each of these 100 threats. We can do it relatively easily. And from the Markov decision processes, if they're not too complicated, the building takes much longer than the actual running. Maybe they run in a few seconds or minutes, depending on kind of how we're setting them up. They could take a little bit longer. But we end up getting scores for each of these threat scenarios we're worried about. We can get a number out of it, or we can get a few numbers out of it. And the thinking is, from those top 100 we got over the last 2 weeks, let's pick out the 5, 6, 7 that gave us the highest scores here in terms of concern about threat. And so it would be the lowest resilience scores. And let's set those up in our high fidelity emulators. So we'll take those threats scenarios that we're most worried about. And then what we'll do is we'll configure Caldera to represent the particular threat scenario we're worried about. We'll add any payloads that we need to represent attack on the system. We'll deploy it in our Scepter model of the system, extract the data, and ultimately come out with a rank ordering of the threat scenarios that we're most concerned about. So let's talk about what this would look like in a particular use case. So one of our recent studies focused on a hypothetical attack for on a SCADA system for a pressurized water reactor in a nuclear power plant. And I'm just going to say up front, this is purely hypothetical. This is not intended to represent any real attack, any real system. If we do that, all of a sudden we're getting really sensitive and we can't talk about things here. So this is the notional attack here. And so what we're going to do is we're going to assume that on the corporate network somewhere, malware has established a foothold on a computer. So maybe I clicked on a link that took me to a bad site and I didn't realize it, but malware got downloaded on my computer. So, but if I'm working on the corporate network, I really have no reason that I should have access to devices controlling the industrial control system. And so there is a firewall typically between the corporate network where the malware has established its foothold and the devices that control that pressurized water reactor. So we're going to assume the malware is set up on one of these devices, and it's going to do network discovery and try and figure out passwords and ultimately pivot through the network until it gets to what we're going to call the IT admin's machine. So this is the one device that actually can tunnel through the corporate firewall into the industrial control system network. And the reason that the admin is trusted to do so is it might need to update patches, it might need to fix some things, it might need to look at it, but they're relatively trusted, and so not everybody gets to go through there. And one of the counterpoints we frequently hear when discussing ICS and this type of attack is, well, our systems are air-gapped, or these aren't designed to be connected to our corporate network. And that's certainly often the case, but very often we also see that maybe we've got a contractor to do system upgrades, and whether we realize it or not, they may have left an opportunity to get over here so that they don't have to fly out to Sandia to make the upgrades. They can just do it remotely. And so what the malware is going to try and do is try and get to the admin machine. It's going to try and harvest the passwords, and from there, it'll tunnel through to a machine on the SCADA network. And from there, it will start sending messages to one of the programmable logic controllers that changes how it operates the pressurized water reactor. And what the attacker goal is it's aiming to actually cause an unsafe condition, cause the pressures, the temperatures, other environments with which the reactor is operating, so that it gets to an unsafe condition and ultimately causes the shutdown. And so we hypothesized a few different dimensions with which we could vary the attack for a scenario. So one would be directness. Is the attacker using insider knowledge and can take a minimal path to that IT admin's machine, or does it not have that insider knowledge and has to bounce around and pivot a lot before it gets there? Does it remember which devices it's infected previously, or is it going to reinfect the same machine multiple times as it pivots around? Was it designed just for Windows machines, or is it capable of doing Windows and Linux? And in this particular scenario, we're assuming the IT admin has a Linux machine. Which of the programmable logic controllers might it be targeting? Is it going to go after the reactor coolant pump? Is it going to go after the steam generator? Is it going to go after both of them? And so just this combination alone here, we've got, through some simple brainstorming, we've got 24 different variations on the attack. And so one of the things we want to know is which ones would be the worst, and that maybe we should think about a little bit more from an emulation perspective. And then also, is it actually possible to get that unsafe operating conditions, and can we force a shutdown through the pressurized water reactor? So I won't go into the details of the mathematical model. What I'll say is whether it remembers what it infected or not, that affects the size of the system. We go from 11 states to 82 states. Whether or not it affects Linux machines or Windows machines or not is going to affect the probability that it can go from one device to another, and how quickly it might be able to do that. And so when we set up our models for a particular system, we had about a dozen machines on the corporate portion of the network and another dozen or so on the ICS portion of the network. The results from the kind of very abstract mathematical modeling, we looked at two different criteria. One was the probability that they could reach the target on the SCADA side. So do they pivot through the network, make it through the firewall, and actually get to the point where they get to deliver the payload? And the second one is, if it does get there, how fast can it get there? And so we can see pretty quickly there's 24 different bars here. There's some that are very small here. These are the ones that are designed only to attack Windows machines. And so we can see they generally don't make it because they have to crack the Linux machine to get through. But the ones that we should worry about are the red and blue bars here. Those are the ones that get there to the target with the highest probability, and they also get there the fastest. And so those are the ones that are using that minimum path, so they have the insider knowledge, and the effect of whether or not they're circling back and remember which machines they infected previously or not doesn't have a whole lot of effect, at least not at this scale. And so what we're seeing is obviously the effect of insider knowledge has a significant impact. But we haven't been able to answer one of our questions, and that question was, could we actually cause the reactor to shut down? And so using this kind of abstract mathematical modeling approach, we're not able to do that. And so what we need to do now is go to the emulation and further specify some of these attacks. And so we refined some of the attacks that were the high concern ones from the mathematical modeling to we came up with 8 different variations. And the key variations is which of the devices are being targeted. And so is it targeting the reactor coolant pump? That could potentially cause it to overheat, and therefore the reactor core would get too hot. We'd need to shut down. Is it affecting the steam generator valve, where we cause it to close when it should be opening up, and maybe we get increased pressure that could lead to overheating and again a shutdown? Are we going to send it some faulty readings that potentially would cause it to operate inappropriately? And so we came up now, these are a higher fidelity type of attacks where it's not just is it moving through the network and how fast, but we're actually targeting specific pieces within the industrial control system. And so once we've specified these additional attacks, now we can look at some of the results coming out of the emulations. So in the top, we have attacks that did not have insider information. So attacks 1 through 4, they took the full path. These were their targets. And then the bottom row is where they did, it's the same type of attack, but, or targeting the same device, but they had the insider information. And what we can quickly see here is if 1 is the most resilient and 0 is the least resilient, attacks 1 and 5 are the biggest concerns. We can also see the benefit of having that insider knowledge. It generally causes bigger problems for the system. And so attacks 1 and 5 are where the reactor coolant pump is being targeted by the malware. And so you can imagine if we see this result, we say, okay, well, why are these so much worse? It seems like all of them could be a problem. So let's start to look at some of the data that we can pull out of the emulations. Here we have a picture of what the temperature is in the physical process model over time. So 0 is when we start the experiment. Each of them runs not quite 50 minutes, almost a little more than 45 minutes. Vertical axis is temperature or degrees in terms of Kelvin. And in the process model that we have, if we exceed 590 degrees Kelvin, that's going to lead to an unsafe operating condition. And so we can see in these two scenarios here, we have exceeded those safe operating conditions. And so we see this is attack 1 right here, in which the reactor coolant pump is being targeted without insider knowledge. And this is where it is being attacked with insider knowledge. And so it's about 12 minutes in before attack 5, we cross this level. And it's about another 20 or so minutes, a total of 24 minutes or so before we can actually do it without the insider knowledge. So immediately we know we've exceeded these unsafe conditions, and what the logic in the physical process model is, it's going to kick in the reactor protection scheme, and it's basically going to force a shutdown. And so if we look at the pressures, we see something similar here too. The pressures and the temperatures spike for the same attacks at roughly the same times. Again, this is attack 5 with the insider knowledge. This is without the insider knowledge, and nobody else is exceeding it over there. So one of the questions that we want to understand is if we know those are the attacks, we certainly should be protecting the reactor coolant pump PLCs, because that's getting the worst or the attacks on the reactor coolant pump PLCs are causing the worst effects from the physical process model. But if we wanted to design intrusion detection and intrusion response, how good do they have to be? How fast do they have to happen? So one of the statistics we can do is we can look at the traffic in terms of packets being sent back and forth between the various devices and figure out how quickly is this attack actually happening. And so one of the things you'll commonly see in attacks on systems, not just ICS, but on IT systems as well, is malware, once it establishes a hole, it may beacon back to an external command and control server. So it can pass exfiltrated data, it can receive new commands, get new instructions. And so the Caldera tool acts like malware in the sense that it has an external command and control server that it's going to beacon back to. And so what we can do is we can track the packets that are being sent to that external server and from where they are being sent and when. And so in this plot, what we have here is on the horizontal axis, we have time of the experiment, and the vertical axis we have is a packet being sent from the SCADA workstation. So this is the machine on the ICS side of of the system where it's going to launch the deployment of its payloads and start trying to affect the programmable logic controllers. And so we can see this diagonal line here is just an artifact of it's trying to connect dots, but it's really at about 12 minutes in is when that first packet for all of the attacks with knowledge start beaconing back into the SCADA workstation. So that can tell us it's about 12 minutes in before it gets to the SCADA side of things, and that's also about when we see the temperature and pressure thresholds being exceeded. And so if it doesn't have the insider knowledge, it takes about 26 minutes roughly. And we see some natural variability here in the different attacks. And so if we are trying to come up with how would we protect the system and make it more resilient, what we know is any mitigation we come up with has to not only detect the attack, but it has to mitigate that attack within 12 minutes. If it can only do it within 15 minutes, by that point, it's too late. And so by using these platforms, not only can we understand what are the weaknesses of the system, but we can start to think what are the requirements that we would need if we were going to develop mitigations for these types of attacks and to protect our systems. So I think with that, I'll go ahead and wrap up. I've been talking for a while here and getting into a variety of different topics. So I think if there's one thing that you walk away with today, is that it's no longer a philosophical question of whether or not industrial control systems are being attacked, whether or not they can be disrupted with cyber attacks. They certainly are. There's plenty of documented literature on it. And so we need these systems to become more resilient. And one way that we're exploring their resilience at Sandia is certainly through the use of models. It's not to replace testing on actual hardware, but as a means to provide another perspective, another means, and to complement that study. So there's a place for the use of mathematical modeling. There's certainly a place for emulation. And on the AdRock project, we've attempted to use them both in kind of this hybrid approach to get the best of both worlds. So we're certainly not done. There's a lot more work that could be done. And, one of the challenges is, what are other modeling techniques that we might want to use? How could we actually come up with parameters for some of the models that we are using? And so one of the current techniques that some of my colleagues are looking at is, can we use reinforcement learning methods to better understand the attacks, to come up with novel attacks, and not just try to look at attacks that have previously happened, but what are ones that we might not have thought about, and how could we build those out? And so I think with that, last thing I'll say is I was the fortunate person today who got to chat and to share our results, but there's a great team that I get to work with on a regular basis. And these folks were directly involved with the AdRock project, but we've got a lot of other great people at Sandia working on this topic.
Eric, thanks so much. Wonderful talk. I was delighted that you saved the best for last, the mention of reinforcement learning, which in my opinion can be used for all things all the time. I'm a little bit over enthusiastic about it. Really engaging discussion, and we had sort of an explosion of questions as you were talking. So we have a big backlog in Q&A. I'll just say that the questions kind of fall into several categories. There are a number of questions about what your various test beds include and don't include, and then there's a broad set of questions that relate to availability, right? What can we get our hands on? So let me turn it over to some particular folks ask the particular questions, but I'll ask everyone who comes on mic to be really brief with the question. If I don't hear Joe, I'll ask it for him. Joseph, forgive me for jumping ahead with this. Then the question that you posed is, what about sensors? So field devices include process sensors which have no cybersecurity. Are they included in Scepter?
Yep. Yeah. So we can, one thing I forgot to mention is we can do hardware in the loop. So if you have a specific field device that you want, we can certainly set that up. With the virtual ones, um, we have generic versions, and sometimes we do have specific, maybe it's a Schweitzer model or some other one. But yes, we do know that many of them are absent of basic security uh, elements. And so we can certainly include those. And if somebody's developing a new one, and we can kind of integrate that, we can also test out what are the benefits of some new one with possibly some improved security aspects.
Great, great. Matthew Martin, you have a couple of questions that relate to both availability and or really what's in some of the systems. Would you like to ask those, Matthew?
Hey, can you hear me?
Yeah.
Oh, awesome. Okay. So let me scroll down to my questions. So yeah, first question I guess I had was the additional payloads and plugins locally developed in Sandia, or if there was going to be available, or those were like open sourced.
Yeah. So the one we used on this particular project was developed at Sandia. There's a nice paper presentation about it. I'll make sure to route that to the conference or webinar organizers. But there is a pretty decent amount of documentation within the Caldera community. And so I would not be surprised if there's additional plugins, kind of depending on what you're trying to do within GitHub.
Got it. And then Matthew, you had a question about Defend, but Defend it was answered by Will Barnum saying Defend is currently not in Caldera.
Right.
Yeah.
Yep. So that's all I had.
Any plans for Defend later to be added into Caldera? Eric?
So I can't speak to that.
Okay.
Caldera is really set up as an attack capability, and that's why the MITRE attack framework, it sits on top of it very nicely. With Defend being focused on kind of the mitigation side of things, it might be an odd fit within Caldera, but I can't say definitively.
Okay. So Joe Matola was asking, can you share a technical paper on about the RevRun and your metrics construction? Is anything like that available? Yeah.
Yeah. So my understanding is the slides are available. So I've got a link there. That conference that we're presenting at is supposed to come out in the next month, but I will pass along that paper since I've got it cleared through RNA to either Peter or the organizers and make sure that people can take a look at that.
Great. Thanks so much. A related kind of question is from Sean Hutton. Sandia is planning to open source Scepter. Is there an anticipated time frame when it will be available for the public? And also, will Manipio be open sourced?
So with respect to Scepter, the last update I got is they're waiting on just one last signature. But they have been waiting for a little while. And so I can't give you a hard estimate on that. I think that if you are a US government partner, there may be opportunities even short of open sourcing where we might be able to share. So that's something that I can look into. With respect to Manipio, I think what I'd probably do is Andrew Hahn was the developer of that capability, and so he lent it to us for use. And so what I perhaps prefer to do, rather than to speculate on that, is maybe connect people who are interested with Andrew, and I can provide contact information for that.
Terrific. So Bill Howell, you have a question and a comment kind of combined about control theory and neural nets and stuff. Did you want to pose that, Bill?
Yes. Oh, thank you. Yes, it's just a very general question, maybe not terribly relevant to most attendees, but for some time, a period of almost 10 years, I was following advanced control theory with neural networks. Uh, is there any thought of applying anything like that within your virtual modeling environment? Or is that just simply off of the mainstream control systems that are actually used in application?
So, uh, as far as neural networks specifically, uh, I can't say with definitive certainty whether or not that's the particular approach. But we do have our funding source for this was kind of through Sandia's internal research dollars. And we have requested kind of the next round of funds to say, can we add some increased intelligence to either the attacker or the defender in the representation? Caldera is certainly a nice, great tool to use, but it is scripted. It's not AI. It's not learning. It's not kind of doing that. And so we are looking at perhaps some reinforcement learning techniques. I'm not familiar with neural nets, um, but I do know it's being studied at Sandia. I would say from linear control theory, I would hope that we can pull on that and add some there, but I can't say definitively that's the direction that we're going just yet.
Yeah, so I'll just add that in reinforcement learning, that that the neural nets would play a major role in the solution techniques to the MDPs that you formulate, or the reinforcement learning. So I think that that'll be natural with your Markov decision processes and your RL framing. Good.
Can I just?
Oh yeah, go ahead, Bill.
The only actual implementation, very sophisticated neural network control system that I saw a presentation of was by, I think his name was Zimmerman, for, I think, Siemens in Europe for controlling electrical grid flows in Europe. So that was it shocked everybody when they saw what they were doing. It was very deep recurrent networks before deep learning became a big issue. A big, I shouldn't say issue, but like a fashion or a trend. The other ones were Kumar Vinayagamurthy and the collaborator at Florida, Kumar's in Clemson, and they had worked for years trying to implement advanced control theory with based not. It's never based only on neural networks. It's always combination. Successful in getting an example grid to actually apply it. I think people are absolutely terrified of the same thing as in aeronautics, because mathematical theorems proving stability and control are not the same in systems like that, very large networks of neural networks.
Good. Okay, we got to move on. So Scott Lucero asked about human behavior, and to the extent that you take, you model operator response, or any aspect of human behavior in the context of what you're doing. Can you give a brief comment on that?
Yeah, so as I was previously mentioning, Caldera is scripted, and the really crude approximation of maybe the attacker human behavior. But we can represent human behavior a few different ways. One is you can actually have humans interacting with these systems and playing defender or attacker. We've done that for power systems. We've done it for oil systems. We actually just delivered one for the Air Force that is being set up for satellite networks. So you could have attackers and defenders kind of on the ground station and networks there. But is that practical? We mentioned that there might be limitations with that. And so what I would say is, for these kinds of test beds, if you can build the tool that represents kind of that learning behavior and maybe that stochastic variability, do they happen to go down this route versus that one? If you can build the tool and it interacts in the same way that it would with the real system, there's no reason we couldn't drop that into this emulation network. That hasn't been a primary part of our particular research effort. It's more kind of setting up the platform where you can plug and play. And Caldera just happens to be the tool that we're using for attack. I will say in our kind of proposed research plan, we're pivoting from the focus on how do we kind of set it up to look at the attack to more on the defense side of things. And so I expect that's where we'll want to understand a little bit more on the human behavior and kind of representing that. I'm not knowledgeable in that particular side, what are the technical aspects to it, but I certainly recognize that is a limitation on these kind of platforms, and how we get there is something where a direction the research needs to go.
Great, thank you. A specific question from emails. What if you have MFA set up, would this mitigate the risk of admin account compromise?
And MFA, multi-factor authentication, I'm assuming that's it.
Yeah.
So, I think there's always the example I set up was intentionally a little bit simple and naive. So in this particular case, it would depend upon, what's the authentication being set up, and then what is the set of tactics and tools potentially being used. So it's a potential mitigation, depending on the assumptions we put in the scenario. I'd also say we know it's not perfect either. And that's where we go back to don't forget about resilience and not just focusing on security.
Yeah, here. David Traub-Warner has a complicated question. David, would you want to pose that one?
Thank you. Can you hear me all right?
Yeah, we got you.
First of all, I want to thank you for the presentation, which has been really excellent and informative. My question is related to standards and current or developing standards, and whether or not those are incorporated in some of the virtual testbed and simulation tools that you've mentioned. And my question really comes from the point of view that clients or infrastructure owners really prefer adherence to standards. So I was wondering if you could just comment as to some of the standards with respect to cyber resilience in industrial control systems, and how they may be incorporated in the work you're doing. Thank you.
Certainly. So with respect to standards, we can build the emulations to spec, and it always depends on, do we have a virtualization of this particular device, et cetera. But, if it's, whether it's how do you configure the firewalls, does it have encryption, those kinds of things, those can be built into the system, so you can build it out to the potential standards. I would say my knowledge of cyber resilience standards, I would say there is not a whole lot out there. I think NIST and MITRE have partnered to develop their cyber resilience. I think it's, I can't remember the NIST number off the top of my head, but it's something like cyber resilience engineering. They piloted a standard. They do a really nice job of outlining the various things that you might want to consider, what contributes to resilience, and across the spectrum of options, what you would consider. But I have not seen any good hard standards that say, thou shalt do X, Y, and Z. Andy McEnroe came up with the right NIST standard there. I haven't seen any that say you need this to become resilient. And if I did see one that said you need this to become resilient, I would be wary because there's always the context in resilience of resilient to what. And as soon as you set up standard that protects you against, 1, 2, 3, then, threat 4 comes along. And so I think the other thing too is different systems have different priorities. And if we're protecting that mission, how you protect that mission is going to vary from one system to another. So I think we do have the flexibility within the test beds to set them up to be representative. What if we followed this standard or set of options as opposed to that one? But I would say, in my opinion, and perhaps it's controversial, I don't think the field is mature enough to broadly adopt and implement standards at this point.
Thank you.
Great. So a kind of related question comes from Carl Middle-Stokes. What steps are taken to ensure the algorithms and models that are developed use somewhat realistic data, go through getting the right data and having some assurance of fidelity? So there are several questions like that. Yeah.
Yeah. Go ahead.
Yeah, because you want to build up those algorithms in that process, and you want it to be a learning process so you can reflect upon it. And you want to have that realism from the industry that that is creating these controls.
Yep. No, that's a excellent question. And as I said at the beginning, there's more and more attacks regularly. But do we really have enough of a data set that we can, with good precision, kind of develop the parameters and the estimates? So as we're building out the mathematical models, some of that is relying on expert judgment. Some of it is based upon what we've seen in the wild. And then some of it comes from running experiments on various different pieces of the attack. We had another effort where we would run kind of some experiments, and based upon that, we could start to develop these model parameters. So a combination of expert judgment, things we've seen in the wild, and then maybe running some experiments on individual pieces of the attack. And that's generally how we'll develop kind of the mathematical model. But that leaves us a little bit short when it comes to the high fidelity. And I think that's also part of the reasonable concerns people might have with respect to just relying on kind of some of the traditional mod sim. There's less parameterization that comes into play with the emulation models when we're setting things up, because then we're following engineering standards and practices. It's the biggest kind of parameterization comes in with how do we configure Caldera or whatever our attack module is, and kind of make sure that's reasonable and realistic.
Thank you.
Good. Couple more questions here. Kelly Edwards, how do you go about attempting to calculate how long any specific attack is going to be successful, Eric? Yeah.
So how long do we take for an attack to execute? Or how do we calculate that?
Yeah, I think that the nature of it is, an attack is ongoing. It's going to affect something, like your oil pipeline, but for how long, right? And the magnitude of the impact is certainly dependent on how quickly you could undo the effect of the attack. I think that's the nature of the question.
Yep. And so, when we monitor kind of how long does it, when we're quantifying how long does it take for an attack to succeed or get to a particular point, usually what we're doing when we're setting up the attack is it's kind of a sequence of activities that might happen. And so we have kind of within the platform, we can extract certain kind of data that tell us, okay, it's hopped from machine 1 to 2, now it's at the admin machine. Okay, now we see that it's on the SCADA side of things. So we can track progress. And what we can do is when we start to look at the physical impacts, under a set of assumptions and conditions, we can watch what might happen. And so with this particular model, the pressurized water reactor model, it was developed by the University of Sao Paulo for the IAEA, and they implemented reasonable reactor protection schemes. So how the system would automatically react to the conditions. And in that case, it's probably fair up until the point where it trips the threshold, and then saying from that time up to that time, it's probably a fair estimate there After that, you probably start to lose some credibility if you're going to say, and now it's 5 days or 2 hours or whatever to respond. One of the areas that I think is really lacking in resilience in general, but definitely in cyber resilience, is that modeling of the react and respond component. So there was a question earlier about the human element, and that certainly comes into play with how might you react, and maybe it's an automated response. But once you've kind of violated some initial threshold, or you start to get too far into, now the whole world knows that something's on fire. If you don't have that built in within your model of what's the response, whether it be human driven or automated, of how do we start to mitigate, once you reach that point, you really shouldn't take too much. You shouldn't infer too much beyond that point. So I think we felt okay saying up until this point, it took this long. And once we hit that reactor protection scheme, you're done. But past that point, I think we would be a little bit uncomfortable with saying how big would it be. And I think that is a caution with all
and I could see how it'd be really complicated in something like Colonial Pipeline, right, where that ultimately the impact was how long the pipeline was shut down, and the shutdown of the pipeline itself was dependent on, well, how many financial transactions are we missing, as this unfolds. So very difficult to understand how an organization would respond to that and get to the bottom of, the high fidelity estimate of impact. Very good. So Mohammed Chami has a question, and I don't know if people are able to get off mute, but Mohammed, if you're able, go ahead and ask it. But otherwise, I'll read it. Do you consider the traceability between a set of model elements of the model elements you showed and other non-cyber model elements, such as requirements, use cases, architecture, et cetera? What is to what extent are you modeling the whole system versus cyber elements? Is that about right? Okay.
Do you hear me now?
Yes, thank you.
Yeah, many thanks. So it's just to consider the non-cyber aspects. There is an enormous information will be influencing the model elements you are considering. So what about the traceability? What about like if something changed in the requirements, or let's say we have a new role on the attack? So are you considering the traceability for all this non-cyber aspect into your cyber aspect?
So I would say one of the things that we definitely do is when we go through this process and we're coming up with conclusions and results and we're passing it on to our sponsors, like any good modeling effort, you need to document your assumptions. And we certainly say kind of under these assumptions and these conditions, we trust these results. And the farther you get away from them, we're not so sure. But one of the things we can do with respect to, is something traceable? Is it actually implemented kind of within the cyber element, or maybe it's something else? Is we will do, we'll change, one or two things within, one run, and then we'll rerun it. And by kind of honing in on kind of these individual changes, we can isolate what the impact of some of these things might be that maybe are not represented directly in the attack, but maybe in kind of the overall system or somewhere in there. We do have some research efforts that are looking to bring in features like weather. So if we're doing like a long analysis, and you might see changes in electric power demand, or so not weather, but that would be temporal, night and day. Maybe it'll go up and down. We want to drive the system up and down. It could be respect to, if there's a larger scale attack, and maybe all of a sudden this one population is no longer around and they're not demanding power, we want to send that drop in power signal to the power system. So maybe you could show the joint effect of kind of two attacks, one not focusing on the industrial control system, directly, but affecting the demand to it. And so we certainly have research efforts that are trying to figure out how do we bring those exogenous variables into this modeling environment. What I'll say is sometimes I think it makes sense, and sometimes it's let's just create a separate model and find a way to pass, some information back and forth.
Very good. Good. So, Joe Weiss, would you like to ask a question about sensors? I think we asked that earlier, but I think it would be great if you can come off mic and elaborate on it.
The fundamental point is our sensors have no cybersecurity in them at all. And that means, that the question is, how do you know you can trust them? And that includes not only the value, like when you're asking, does the reading make sense, but the settings. So the issue is everybody's concerned with the programmable logic controller, but the sensors can actually brick the programmable logic controller, and there's no way for you to know it. Or the sensors can be changed so that they don't initiate any safety systems.
Yep.
How are you going to address these kind of issues?
And so I think everything you've said is entirely valid. And I guess what I would say is what we can do within these emulation capabilities is we can demonstrate what you've shown or what you've described. And if there is, some capability that affects the reading coming out of the sensors, or is there a mitigation that we could potentially use to protect against that, and test how actually effective is it? Within these platforms, we can start to evaluate, is this a real threat or not? And is this mitigation potentially effective or not? But unfortunately, I'm not the subject matter expert on, how would we go about actually protecting these systems to do that. There are other folks at Sandia that could probably provide you a better answer on that. But what we can do with these platforms is we can show here is how significant an impact it could potentially be, or maybe we don't need to worry about this as much. And so that's a little bit of a limitation of my background and perhaps the platform. But there are certainly people, I would say, my colleagues that are looking at that, and it could potentially connect you with people who could better answer that if that's a topic of interest.
Thank you.
Great. And Joe Matola asked, are there any opportunities for applying ad hoc type approaches to water treatment facilities? So if there's a yes to that, then we want to get Joe to amplify that question. So Eric, any path?
Yeah. In this particular case, we had a model of a nuclear power plant. But if you could swap in a water treatment facility and do comparable types of investigations.
The first is
Joe. Yeah, there we go. Joe's on. Okay. That was one question of mine, Eric. I guess it occurred to me when looking at a Scepter in particular, and just thinking about from a resilience perspective, I might want to have the ability to take a system, and I don't know if this is on the real system or one level down, but to not view it in terms of I'm going to put in attacks, but to say, let me, from a purely resilience perspective, let me just, cut out system functions, just turn things off, in a way that might not be possible, or there might not be in the real system, interfaces for doing that. Right? That wasn't part of the way the system is supposed to work, that you're able to turn off this thing. But it could be a plausible effect of some cyber attack. And the advantage of doing that maybe is that then you don't have to think of all the pathways to get to that point of turning off that function. But it would seem to require some specialized emulation or control capability to be built into the system just for those kinds of tests. So something that's not maybe the real system, but one level down in terms of it's there, we can manipulate it in some kind of way. Have you thought along those lines at all?
So I think actually what you're describing is easier than using Caldera. So basically, can we just turn off a functionality or a device, something like that? Actually, also the underlying platform that is Scepter and brings all of these things together, there are very simple. You can type it in, you can script it, but there's kill commands, there's sleep commands, and
Yeah.
so you can certainly do that type of thing. That's far easier.
Okay.
Scepter has nice little hooks like that you
Yeah.
can set
Okay.
up.
Okay. Good. Excellent. All right. Well, I think we've kept everyone over time, and much appreciate everyone's patience, and much appreciate your talk, Eric, and the the enthusiasm and interest it has garnered among the SERC audience. So thanks so much for joining us today and sharing everything. I think you have a lot of people that are interested, so they'll probably be barraged with emails. So thank you again. I really appreciate it. Okay,
I
maybe.
appreciate the opportunity.
But we hope everyone can join us for the next SERC talk that's scheduled for April 6th with Dr. Alexandra Cott. And thank you again, Peter and Eric, for your time, and everybody else. We'll see you soon.
Thank you.
Thanks,
Bye-bye.
everybody.